All right, so now we're going to ask questions in a backwards way. We're given here the graph of the derivative of f, not f itself. So make sure that's clear in your brains because that's what makes this difficult. So then we're using the graph of f prime to answer questions about f. So for example, where is f increasing? Well, f will be increasing wherever the derivative is above the x-axis. So that's going to be on the interval from 3 to 6. And then they ask, where is f decreasing? Well, that's going to be where the derivative is below the x-axis. But interestingly, we have to include the endpoints here because the derivative is clearly below 0 at both of these endpoints. So the decreasing intervals are going to be from 0 to 3, union 6 to 8. Notice that we have included the endpoints of 0 and 8, but I have not included the endpoints of 3 and 6. So we are allowed to include the endpoints of 3 and 6 if we want. We could have included them in the intervals of increasing. We could have included them in the intervals of decreasing. Quite frankly, you'll never be graded on that. And the reason why is because people argue that, let's take a look at this function here, that as we go up, this interval is increasing and it includes the apex up here or the turning point. Other people say this is where the function starts decreasing, so we should include it here. And other people say at this turning point, the function is neither increasing nor decreasing. So it's really up to you whether you include turning points in your intervals of increasing or decreasing. What you do not have an option about is the endpoints. If the derivative is very clearly one sign or the other, those must be included with hard brackets. So keep that in mind because that generally does come up sometime later in the course, and we will remind you of that as we go. Now, where does f have a horizontal tangent line? That will happen anywhere where the derivative has an x-intercept. So that will just be at x equals 3 and x equals 6. Now they're asking, where does the function f have a local max? Well, that will happen wherever the derivative changes from positive to negative. Because if the derivative is positive, the function's increasing and then moves to negative, now decreasing. So it must have touched a turning point or a local max. So at x equals 6, there's a local max. A local min is going to occur where the derivative changes from negative to positive because the function must have decreased and then increased. So the local min is going to occur at x equals 3. The next question is, where is the function concave up? And that is going to occur wherever the derivative is increasing. So let's take a look at where the derivative is increasing. I see an interval here, and I see an interval here, and I see an interval here. So I've got 3 intervals on which the function is concave up. So that's from 0 to 1, union 2 to 4.5, and keep in mind these are domains that I'm giving you, so they're all x values or intervals on the x-axis, and then 7 to 8, that is concave down. Now for concave up, we want to look where the derivative decreases, so that's here and that's here. So that's going to be, concave down is going to be from 1 to 2 on the x-axis, and union 4.5 to 7. Notice that for my intervals of concavity, I do not include any of the endpoints and I do not include any of the points of inflection where we change concavity. That is a rule that you must follow. You can never include endpoints of intervals or even endpoints of the entire function in your intervals of concavity because by definition, at a point of inflection, there is no concavity on a function. So keep that in mind, whereas when the intervals are increasing and decreasing, you have a choice of including or not including the places where there is a turning point, but a point of inflection may not be included as either concave up or concave down. So where are there points of inflections on f? That is going to be wherever the derivative has turning points. So I see 4 of those points, and that actually makes sense because it matches these intervals on which we switch from concave up to concave down or concave down to concave up. So that will be at x equals 1, x equals 2, x equals 4.5, and x equals 7. Next question, when does the function achieve its maximum value on the interval from 0 to 2? Well, on the interval from 0 to 2, the derivative is always negative. So what that means is that if the derivative is always negative, the function must be always decreasing. So its maximum value will occur at the left-hand endpoint. So that is going to be at x equals 0, because from there the function decreases. On that same interval, where will the function reach its minimum value? Well, that will be at the right-hand side of the interval at x equals 2, because again, on 0 to 2, the function is always decreasing because the derivative is negative. So now let's look at the interval from 3 to 6, which is up here. Where will the maximum value be? Well, on this interval, the derivative is positive, which means the function is increasing. So that means the right-hand side of the interval, x equals 6, is where the max value is achieved. The min value is achieved at x equals 3 because the function increases from 3 to 6. And then the last part, or second to last part, says let's assume that f of 0 is 0. Let's go ahead and sketch a graph of f given the antiderivative graph. So this is going to be tricky and take a little bit of time, so we're going to work through it together. I'm told an initial value, a starting point here. Now I see, and I'm going to separate my derivative function into different sections by turning points, which of course are points of inflection on my original graph, and x-intercepts, which will be places where my original function has horizontal tangent lines. So just like when I graphed a derivative function, I'm going to graph an antiderivative by looking section by section. So I now have 1, 2, 3, 4, 5, 6, 7 sections to graph. First, my derivative is negative but increasing. So my function is decreasing but concave up. Then my derivative is negative and decreasing. So my function is going to be decreasing but now concave down. So you see I have an inflection point at x equals 1, which matches the turning point on the derivative. And for the next section, my derivative is still negative but now increasing. So my function is still decreasing but now concave up. Next, for my next section, my derivative is now positive, and then it is still also increasing. So my function now needs to be increasing and still concave up. And notice that I created a horizontal tangent line here at 3, which matches the x-intercept on the derivative function. For the next section, my graph of the derivative is still positive, so my function is still increasing, but now the derivative is concave down. So, now my derivative is decreasing, so my function needs to be concave down. So I go like this. Notice how I created an inflection point on my function, which matched my turning point on the derivative. Now for my next section, my derivative is negative, so the function will decrease, and my function is decreasing. My derivative is decreasing, which means my function needs to be concave down. So I've got a decreasing and concave down function. Once again, I created a horizontal tangent line, which matched the x-intercept on my derivative. And then my last bit here, my derivative is still negative, but increasing, so my function will still be decreasing, but concave up. And then the very last question on the page says, how does your answer to part 8 change if your initial value was 5? Well, the only thing that would happen is I would have started up here at 5 instead of down here at 0, and I would have shifted the entire antiderivative graph up by 5 points.